In the last video of the tiny tool grinder, I discussed the desirability of a quick change system for multiple grinding wheels. One of the problems is that each grinding wheel must then be correctly balanced beforehand. In this video, a report of my attempts to do so. The first question I asked myself was, what standards should I use? Instead of experimenting myself, I started from a well-known ISO standard, which states that the correct value for grinding stones is 1 gram times millimeters or better. That is a torque, just like the Newton meter. It is a very small torque, but that's necessary to ensure low vibration at high rotational speed. This is the test setup. 2 horizontal smooth ground straight shafts were leveled very precisely, and the grinding wheel to be tested was placed on a very straight shaft. It soon became apparent that the shafts were not smooth enough after all. The rolling shaft regularly stopped prematurely due to a micro-groove barely visible even under the microscope. So I ended up using 2 carefully degreased small ball bearings, but left the setup unchanged. This also provided an opportunity to see what offered the least rolling resistance. After doing these tests several times, I determined the position in which the center of gravity of the disc was vertically at the bottom. With small blobs of putty placed diametrically, I tried to balance the disc as accurately as possible. And when the most accurate counterweight was finally found, the weight of the blob putty was determined in milligrams. The diameter of the disc in this case is 78 mm, so that the radius to the center of the blob is almost exactly 40 mm. In this case, the torque required to balance the disc is therefore 40 times 135 mg. That amounts to 5.4 grams times millimeters. In this way I have determined the size and location of the deviations from the perfect balance of all discs. This table shows the results of the measurements, as well as a brief summary of the formulas used and the requirements for the various grades of the ISO standard. It is clear that balancing is really necessary. The deviations are around 10 times higher than is allowed for grade 1. In the right column I have calculated how much of the steel I have to drill away to restore the balance. One factor is still unknown, and that is the accuracy of this measurement setup. For this I first tried to determine the minimum force with which I could get a balanced disc spinning again. For this I used pre-made blobs of putty and searched for the smallest amount that was enough to get the whole thing running again. This method was not very successful. It just took too long and was too crude. During testing I noticed that the central shaft usually did not move. Apparently the rolling resistance in the small ball bearings was slightly less than that of the shaft on the bed. But sometimes, especially at very low rotational speed, it started to roll. Apparently the rolling resistance of that axle can be lower than that of the bearings. I ended up using a more statistical approach to determine measurement sensitivity. I let the discs come to a stop 30 times and drew a dot at the lowest point with a marker. And so I reached a measurement inaccuracy of plus or minus 28.5 mg times 40 mm. That amounts to a little more than 1 gram times millimeters. And that is equal to the minimum allowable imbalance according to ISO grade 1. So at the moment I am not able to achieve the required accuracy. But the sometimes rolling axle does give me a way out. I'm going to carefully lap all 3 axles to remove all microscopic grooves and obstacles. I suspect that, once done, the rolling resistance can drop so much that the measurement accuracy will be within the requirements of grade 1. But now I first have to wait for the ordered lap paste to arrive. So, I hope you learned something from this video. See you next time.